Alright, let's solve this problem based on the modified Brighton cycle, right, that used in an automobile. So here it's saying that a gas turbine for automobile is designed with a regenerator, right? So this part is basically a regenerator part right here, and then all those basic conditions or all those conditions are given. For example, the compressor inlet pressure and temperature is given, and then compressor pressure ratio is given. So the maximum cycle temperature is 800, which is the outlet of the combustor, right? And then one of the most important thing about this problem is that, this statement, the cold stream leaves the regenerator 10 degrees C cooler than the hot air stream at the inlet of the regenerator. So we have to use this statement to determine the temperature at T3 and T6, right? So basically it is asking us to determine the heat addition Q in and heat rejection Q out of this cycle. So let's draw the TS diagram, which eventually will make easier to solve this problem. So the TS diagram of this particular modified Brayton cycle or gas turbine cycle will look like this. So 1 to 2 is the compressor, and then 2 to 3, it's basically heat is adding to that working fluid, right? So this is 2 to 3, and then 3 to 4, it will gonna experience the maximum temperature, right? So this is 4, and then 4 to 5, it's expansion, meaning the temperature is decreasing, right? And then 5 to 6 is also rejecting some sort of heat in this heat exchanger, so it will decrease the temperature. So this is 6, this is 5, and then from 6 to 1, again it's coming to that initial condition, right? So this is our basic TS diagram. So here it's that Q regeneration, however here is the heat addition Q in, and here is the heat Q output, right? So this is the most important thing about solving this problem. So now let's go ahead and take a look for the compressor, what are the things is given. So for compressor, pressure is given, P1 equals to 100 kilopascal, and then T1 equals to 30 degrees Celsius. If we convert it to Kelvin, it will gonna be 300 Kelvin. And then the pressure ratio RP was given, which is 10. Now we know that by the definition of pressure ratio, we know that RP equals to P2 divided by P1. That means pressure after the combustion and pressure after the compression and pressure before the compression, right? Which is equals to 10. So from this relationship we can write P2 equals to P1. Basically it will become Pascal. Okay, so that's our P2. Now for another important thing about, so we know that the P2 and T2 for the compressor, right? So to determine the, basically if we look at this diagram, to determine that Q in, here we need to determine the temperature, actually the temperature T3 and T4. So T4 is already given, which is the maximum cycle temperature, 800 degrees C right here. However, we don't know the T3. So to determine the T3, we have to use some sort of like information here. So basically for this cycle, so for this cycle, this information is given that cold air stream leaves the regenerator 10 degrees C cooler than the hot air stream. That means that this T5 or this T3, the leaving regenerator leaving the temperature, the working fluid leaving or the air leaving the regenerator T3 is equals to this T5, right, which is the incoming, minus 10 degree C. So that's what is the statement here. This equals to T3, but we don't know what is the temperature of T5, so we have to determine the T5, right? So T5 is basically happening in between these states, the turbine, so T4 and T5. So let's take a look how to determine that T5. So if we for turbine if we analyze the turbine, then we'll get this relationship: T5 divided by T4 equals to P5 divided by P4, which is equals to K by K. Now interesting thing about here, T5 T4 equals to, this will be P1 and this will be P2, so K minus 1 and K. How? So here important note is P5 equals to P1 and P2 equals to P4 equals to P2. How? So when the turbine is expanding all those air, or of this compressed air, when it's expanding, then it's coming to the atmospheric pressure, which is 100 kilopascal, and then basically there is no pressure is increasing in the heat exchanger or this 6, so it's becoming the P5, it's basically becoming that P1, it's coming to the atmospheric pressure, because heat exchanger, it's not changing the pressure, and this device is also not changing the this particular device is also not changing the pressure. That means P5 and P1 is the same, and then P4 and P2 it's also the same. It's because of the heat addition and the combustor. We know that this heat addition is a constant pressure heat addition. That means that since the heat exchanger is not changing the pressure, that means P2 equals to P3, which is equals to P4, right? Because all of them are constant pressure heat addition or heat heat exchanging. So by knowing this, we can determine that T5, which is T4 times P1, we know that this is 100 and P2 1000, right, to the power 1.4 minus 1, 1.4. So if we solve this, then T5 will become 5 Kelvin, right? So now the statement it is saying that T3 is 10 degree cooler than the incoming fluid on the regenerator, right? So which is T5 minus 10 degree 10 degrees C. So if we convert it in Kelvin and plug in all those information, then it will be 545.75 Kelvin. So now we know that T3, right? So the question number 1, it's asking us what is the Q in, right? Q in heat addition rate. So it is asking us the rate. That means that we have to determine in kilojoule per second, right? So to determine the kilojoule per second, the formula is Q in equals to mass flow times Cp times T4 minus T3. But we don't know the mass, so that's one important thing. We don't know the mass, right, of this system. We don't know the mass. So how can we determine the mass? So first thing we have to do, we have to use the information of W net, right? So let's determine that. Let's determine the turbine work, WT, right, which is equals to Cp times T5, actually T4 minus T5. So the turbine work, we know all of this information, 0.15 kilojoule per kg per Kelvin, right, times T4 800 degrees C. If we convert it in Kelvin, it will become 1073 Kelvin minus T5, we just determine it, 555.75. So WT basically 519.83 kilojoule per kg. Similarly, WC for compressor work, Cp times T2 minus T1. So WC equals to 1.005. T2, we know that this is so I think we have to determine that T2 from this relationship, right? So for isentropic case, T2 divided by T1, P2 divided by P1 to the power K, K minus 1 divided by K. So T2 equals to T1, P2 divided by P1 equals to 10, pressure ratio equals to 1.4 minus 1 divided by 1.4, and we know that T1 equals to 303 Kelvin, right? So T2 will be 585.001 Kelvin. So that's our T2. So basically let's plug in all this information. 585.001 minus T1 equals to 303 Kelvin, right? So WC will become 283.41. Again, it will be kilojoule per kg, right? So now the net work was given, W net was given 115 kilowatt, right? So the mass will be, right, mass flow rate will be, the mass of that system is basically will be, it will be mass only, W net divided by small w, right? Net output divided by W net of this system, net output, right? So basically 115 kilowatt. So instead of kilowatt, we can write it kilojoule per second, right? So we'll write it later. So, and this one will be 500, 519.83 minus 283.41 kilojoule per kg. So I'm just writing it one more time. It will be kilojoule per second. Instead of kilowatt, we can write it like this, and then it will be 519.83 minus 283.41 kilojoule per kg, right? So this kilojoule and kilojoule will be omitted, so it will leave only mass equals to 0.048 kg per second. So now we know the mass. So now let's plug in to the information one. So Q in, basically number one, mCp times T4 minus T3. So we know all those information. 0.48 actually, 0.48 times 1.005 times T4. We know that T4 equals to 1073 minus 75 Kelvin. So now this Q in will be expressed in terms of kilowatt, 258.3 kilowatt, right? So number 2 is asking us that what is the Q out or heat rejection of that system. So the Q out formula, heat rejection is happening in this cycle. It's basically right here. So from 6 to 1, here is the heat rejection or heat out is happening, right? So the Q out equals to now we don't know the temperature T6. What is that temperature, right? So we have to determine that temperature. How? So let's draw that heat exchanger, right? What is happening? So this T2 here and T3 is here, and then T5 is incoming, right? And T5 and T6 is outgoing, right? And this heat exchanger, so we know all those information. So basically, can we write like this equation like this way? T6 minus T3, which is outgoing temperature, equals to T2 plus T5, which is incoming temperature, right? So from this expression we can write T6 equals to T2 plus T5 minus T3, which is nothing but, let's plug in all this information. We know that the T2 equals to 585.001 plus T5 equals to 555.75 and T3 equals to 545.75. So if we plug in all this information, then T6 equals to 595.001, right? So this is our T6. Now just plug in the value. Q out equals to mass 0.4. Let me write the formula one more time. Mass times Cp times T6 minus T1, 0.48, 1.005, 5.001. So the Q out 52.62 kilowatt. So that's the answer of this cycle. Okay, so that's all about this math problem. Basically it is asking us to determine that heat addition and heat rejection, and we determined the heat addition and heat rejection. So that's all for this problem. We'll come back with the new video. Thank you.